We're going to continue with chapter 9 and significance testing and shift into section 9.3, which is significance testing for a mean. So very similar to what we saw in the last section when we dealt with proportions, and similar to what we saw in last chapter when we shifted from proportions to means. So you see that these things are starting to add up. You have to be able to recognize, am I talking about a confidence interval? Am I talking about a significance test? Is it a proportion type problem? Is it a mean type problem? So just like in everything that we've done so far, we have our three conditions that we need to check. First condition is that same randomness condition that we've seen, whether it's proportions or means, random sample, or random assignment. Then we have our normality condition. You have to make sure you differentiate the proportion conditions and the mean conditions. Proportions, we have n times p greater than or equal to 10, n times 1 minus p greater than or equal to 10. For the means, we have our central limit theorem. N has to be your sample size greater than or equal to 30. If that's not the case, and the population is normally distributed, you're good to go there. If that's not the case, and your sample size is less than 30, that's when we graph our sample data and we want to show that there's no obvious or major skewness or outliers. So same conditions that you saw when we did with confidence intervals for means. And then if we have random sampling, and only when we have random sampling, we are looking for that independence condition. So either independent trials or your sample size has to be less than 10% of the population size. Just like when we did confidence intervals for means, there are two different types of test statistics that we can deal with. We're almost always going to be using a t-test statistic, okay? Because your population standard deviation is going to be unknown. This formula is not on the formula sheet per se. You can kind of piece it together. It is your t-test statistic is equal to your sample mean, x bar, minus your hypothesized value of mu, divided by the standard deviation over the square root of n. And if we look at the formula sheet, you'll see that the test statistic is defined here as your statistic minus your parameter divided by the standard error of the statistic. And if we look at means, we know that if we're looking at a mean problem, here's our standard error of the statistic formula. So we know that part in there. And then our numerator is just our sample mean minus our population mean, or our hypothesized mean, I should say. In the extremely rare case that you would find a z-test statistic, which is not going to happen, okay? The only difference is in a z-test statistic, you know the population standard deviation, so your numerator would remain the same, but this is going to become a sigma over the square root of n, and you would replace that with the population standard deviation. No realistic test is going to be based off of a z-test statistic for means. Similar to what we saw with intervals, when we're talking about how you find the p-value of a calc or a p-value for this, we use degrees of freedom of n minus 1. And then we can use the t-chart, table B, or t-CDF on the calculator. If we use the t-table or table B here, what you're going to see is you're never going to get an exact probability or an exact p-value. You're going to find that it's in between this and this, or it's in between this and this, or so on and so forth. If you use t-CDF on the calculator, which is under second and vars, then you go down to number 5, which is t-CDF. You can get the values that you're looking for here by using t-CDF. You can get the p-value here by plugging in your lower, your upper, and the degrees of freedom. And I'll show you how to do that. In addition, for every mean test, you can just run the entire test on the calculator, similar to what we saw for proportion problems. So if you go to stat and over to test, right, what have we used so far in there? Oops, stat and over to test. Stat over to test. You know we've done a one prop z test in the chapter. We've also done a t interval. Now what we're going to be focusing in on is a t test, and you can run the entire test on the calculator. But I do want to show you how to go about doing this by hand. So let's take a look at that first example that we have here. And I'll work through this example with you here. So, hold on. Let's get down to that example. Alrighty. So, Abby and Raquel like to eat sub sandwiches. However, they notice that the lengths of the 6-inch sub they get at their favorite restaurant seems shorter than the advertised length. To investigate, they randomly select 24 different times during the next month and order a 6-inch sub. Do the data provide convincing evidence at the 0.10 level that the sandwiches at this restaurant are shorter than advertised on average? So that's the key thing where you're going to be getting your hypotheses from. They say it's a 6-inch sub. They don't believe it. They think they're shorter. That's the key word here, where we'll base our alternative hypothesis on. So let's go through the same state, plan, do, and conclude steps that we saw before. So step 1 is state. Let's state our hypotheses and define the parameter of interest. So in stating the hypotheses here, my null hypothesis is that mu is equal to 6 inches. That's my initial claim, what's said to be true. And what they think is that they're shorter. That's the key word there. So that's why my alternative hypothesis is less than 6 inches, as we see here. What does mu represent? Mu is the true mean length of all sandwiches at this restaurant. Notice it's the true mean length of all sandwiches at this restaurant. Significance level is 0.10. We're running a one sample t-test for means. Let's check our conditions. Condition number 1, was it a random sample? So if we're taking a look here, we see that it says they randomly selected 24 different times. So our randomness condition is met. Problem here, our sample size is only 24. So because we have a sample size below 30, doesn't tell me the population is normally distributed. I have to graph our sample data as I've done here. So make a quick sketch of your data. Dot plot works. There's no major skewness or outliers in this data set, so we can proceed on. Step 3, independence condition. Notice, 24 sandwiches is clearly less than 10% of all sandwiches that are out there. Now I have to actually run my test. In order to run my test, if I'm going to do it by hand, I need to find the mean and the standard deviation for my data set. And if I'm going to use the calculator, I need to do the same thing as well. So we have data here. We're going to go to our list, stat edit, and we're going to put our data in. So let's clear out that old data and let's enter in our new data by just plugging in our data set there. Oops, 6.5. Okay, 24 things in there. Perfect. So if I want to do this by hand, I need to find the mean and the standard deviation. So I would go to stat and calc and one var stats. Nothing in my frequency list there. So let's get rid of that L2 and go ahead and hit calculate. You'll get your mean, 5.677. And we were looking for SX, which is 0.657 in here. If you were to do this by hand, okay, and then I'll show you how to do it on the calculator. So if we were to do this by hand at this point, we have our sample mean, we have our sample standard deviation. We can find our t-test statistic by taking the sample mean, 5.677, minus the standard deviation, or minus the hypothesized mean of 6, divided by the standard deviation over the square root of n. So 0.657 divided by the square root of 24. If I do that, I'm going to get a t-test statistic of negative 2.408. That is my t-test statistic. I can then use table B to estimate the p-value by going to degrees of freedom of 24 and looking where 2.408 would fall in between. It's going to fall in between these two t values here. Doesn't matter that it's negative. Okay, so it's going to fall in between these two t values here. And then if I go up to the top of my table, I see that it's going to be between a p-value of 0.01 and 0.02 based off of that test statistic there. Okay, now you can use the calculator as well. So we've found our test statistic. If I go to stat and then go to, second bars rather, and then go to TCDF, I'm looking for the area below, because it's less than, a t-test statistic of negative 2.408. So I'm going to make this a really big negative number. My upper bound would be negative 2.408. Degrees of freedom here is 23. Go ahead and hit paste. Oops. Negative, sorry. I used the minus sign by mistake. And there you go, there's your answer. Now, if I'm going to use the calculator to run the entire test, which is my suggestion to you, I'm going to go to stat, over to tests, and I'm going to run a t-test. I inputted data in here, so I can just leave it as data. Then I'm going to change this. My hypothesized value is 6. That's what mu sub 0 represents in the calculator. Keep L1, keep this, and we're looking at a less than. You can either draw and see the curve, or you can hit calculate. And there you go. There's your p-value again. So 0.0122. Okay, so same thing that we got using any technique that we wanted to. It doesn't matter which way you go about doing it. Any of those would be correct. In my notes, I actually wrote the wrong p-value in here. So make sure that you correct it. Okay, the test statistic is right, but the p-value that I wrote here was wrong. So we want to make sure that we change that p-value in our notes to the correct one, which should be 0.01. What was it? 0.012. So I have to change my notes here. We still end up getting the same conclusion in here. So because our p-value of 0.012 is less than the significance level of 0.1, we reject the null hypothesis. Therefore, we have convincing evidence that the true mean sandwich length is less than the advertised length of 6 inches. So that's the process that you want to take. Again, you can go ahead and you could do it by hand, get the t-test statistic, and then go to TCDF on the calculator if you're one of those people that like to do it by hand. Or you could use table B to get an approximate p-value. Or you can just run the entire test on the calculator by going to a t-test. Again, as I said, you can certainly use it, not t-interval here, t-test. You can certainly use the calculator, just run a t-test in doing that. Okay, that's perfectly fine, and we'll go through this next example in class. Make sure if you're using the calculator, you still must label your test statistic t, you must label your p-value, and you must label your degrees of freedom. As always, you have to check the conditions, and you must name the test as well. We'll do this example in class. So there is a relationship between a two-sided test and a confidence interval. When we're looking at significance tests, okay, we have for means, we have our t equals x bar minus mu sub 0 over the standard error of the statistic. Same thing for proportions. Here's the corresponding confidence intervals that go with each of those. The relationship here between your confidence interval and your significance level is one of like an inverse relationship, okay? And this works for two-sided tests only. So for a two-sided test, okay, if we're talking about the 0.05 significance level, that's related to the 95% confidence interval. And they give us similar information about the population parameter. This is what we saw earlier in one of our examples. For example, if I have mu is equal to 6 and mu is not equal to 6, it only works for the two-sided test. And my interval is from 4.2 to 5.8. What that means is, in this particular case, Notice that 6 is not in the interval, so I would reject the null hypothesis that mu is equal to 6, and I would have evidence that mu is not equal to 6. And that's what that next bullet is saying there, okay? When the two-side significance test h sub 0 mu equals mu sub 0, then the corresponding confidence interval will not contain that value of mu, which is what I just showed you there. If our interval, say, went from 4.7 to 6.3, then the mu sub 0 value is in our interval, and we would fail to reject the null hypothesis. We're going to look at an example that follows here that deals with paired data. This is a really important type of test, so I want to spend some time in class going through this example. If you want to write it ahead of time in your notes, that's perfectly fine. But we're going to spend some time looking at paired data, where we actually have either one person receiving both treatments, or we've paired them up like twins or something like that. And we're going to look at a slightly different version of a mean significance test that deals with paired data in class. Continuing on, though, let's fill in some other things in the notes. With paired data, those are what we're dealing with as comparative study. And a lot of times they're more convincing than a single sample study. So it's a really important thing for you to understand. For that reason, one sample inference is less common than comparative inference. That's study designs that involve making two observations on the same individual, or one observation on each of two similar individuals, like I was saying, which is paired data. In that particular case, we're looking at the differences in each pair, and we're looking at the mean difference. So for example, what was your mile time after you drank a cup of coffee, and what was your mile time when not drinking a cup of coffee? Okay? That way, we're not just saying everybody drink a cup of coffee, and I think that your mile time is going to be less than 7 minutes or something like that. So now I'm making that comparison and looking at the mean difference. On average, what is the difference in somebody's mile time when they drink a cup of coffee versus when they don't? We'll look at several examples in class like that. So now we've done these studies, how do I use them wisely? Okay, carrying out a significance test is often quite simple, especially if you're using a calculator or a computer, but it's using that information that is key. Here are some key things to keep in mind as you're doing this or looking at significance tests. A smaller significance level requires stronger evidence to reject the null hypothesis. The closer your significance level is to 0, the smaller your p-value is, meaning the closer it's going to have to be to 0 in order to reject the null hypothesis. So a smaller significance level will lead to stronger evidence. Higher power gives us a chance of detecting a difference when it really exists. So the higher the power, again, similarly, the stronger your results are. At any significance level and desired power, detecting a small difference between the null and alternative parameter requires a larger sample size than detecting a large difference. So if we increase the sample size, it could also result in stronger evidence, providing a stronger p-value. When a null hypothesis can be rejected at the usual levels of either 0.05 or 0.01, there is good evidence of a difference, but that difference may be very small, especially when we have large sample sizes. So if we have a large sample size, a small difference might result in statistically significant results. If we have a smaller sample size, then we're going to need to compensate that ability to reject the null hypothesis by having a larger difference between our mu sub 0 hypothesized value and our sample statistic. What is the difference between statistical and practical significance? Statistical is purely mathematical. It's theoretical, it's a little bit abstract. Practical significance is fragile. It's subject to poor design, sampling methods, and outliers, okay? So something might seem like there's statistical significance, but in reality, there might be something else going on. It's always important to look at the study design, look at the sampling techniques that were used, look if there's any extreme outlier that's affecting that test statistic when we're looking at the conclusion in our results. The problem with multiple tests is that people analyzing the same data over and over are manipulating the data in order to find statistical significance. Lots of times, you have to be careful about the person who's doing the research. Did they do something that might affect the data so they could just increase their test statistic and show statistical significance? Okay, oftentimes that results in unethical behavior and proves very little. So it's always important to look at the study design, look further into the research and not just look at the p-value alone, because it's easy to manipulate that p-value or that significance level in order to provide evidence to reject the null hypothesis and therefore have evidence of the alternative. I know there's a lot here. We're going to do lots of examples of running different types of significance tests, but that's all for chapter 9. See you in class.